Let's look at OpenStax University Physics Volume 2, Chapter 8, Problem 69. Three capacitors have capacitances of 8.4, 8.4, and 4.2 microfarads, respectively, are connected in series across a 36-volt potential difference. What is the charge on the 4.2 microfarad capacitor? B. The capacitors are disconnected from the potential difference without allowing them to discharge. They are then reconnected in parallel with each other with the positively charged plates connected together. What is the voltage across each capacitor in the parallel combination? All right, so let's write down our knowns and unknowns. We know that C1 equals C2, and that's 8.40 times 10 to the negative 6 farads. We know that C3 is 4.2 times 10 to the negative 6 farads. And we know that the EMF provided is 36.0 volts. And in part A, we know that we have a series combination and we're looking for the charge on the third capacitor. So Q3 is what we want. In part B, now we're connecting them in parallel, and we're looking for the voltage on each of the capacitors. So let's draw the diagram for the first part. We have three capacitors in series connected across a 36-volt battery. So this would be C1, C2, C3, and this is the EMF. Now we have to think about the theory. What do we know about capacitors in series? Well, we know that the battery provides a current that deposits charges on the capacitors, and we know that in series, all the charges are going to be the same. We have the same current flowing in a series combination. That means that all the capacitors will have the same charge placed on the capacitor plates. Furthermore, we know that the charge on capacitor 1, 2, and 3 is the same as the charge across the equivalent capacitor formed by C1, C2, and C3. So I'll write this down. I know that Q on 1 is equal to Q on 2 equal to Q on 3 is equal to the Q on the equivalent capacitance. And that is just CV, where C is the equivalent capacitance, and in series they add as 1 over C1 plus 1 over C2 plus 1 over C3, but that is 1 over the equivalent capacitance. So I have to raise this to the negative first power times the voltage, which we have an EMF here. So that will be 1 over 8.4 microfarads in the interest of saving space, plus 1 over 8.4 microfarads, plus 1 over 4.2 microfarads times 36 volts. And we end up with the charge on capacitor 3, which is the same as the charge on capacitor 2 or 1, being equal to 7.56 times 10 to the negative 5th coulombs. Now in part B, we're taking these three capacitors with this amount of charge, so each one of the capacitors has 7.56 times 10 to the negative 5th coulombs across it, and we are connecting them in parallel. So we have C1, C2, and C3. Now what we know about parallel capacitors is that they have the same voltage across them. So we'll say V1 equals V2 equals V3. So what this means is that the charges didn't stay put as 7.56 times 10 to the negative 5th coulombs on each of these capacitors. They moved around so that the voltage across C1 was equal to the voltage across C2 and was equal to the voltage across C3. But the sum of the charges on the three capacitors has to be 3 times this. So let me write that. So I know that Q1 plus Q2 plus Q3 is 3 times, I'll just call it Q, the charge from part A. Then I know that the voltages are equal, so I'll rewrite this equation as, so since Q equals CV, V is Q over C, so then I have Q1 divided by C1 equals Q2 divided by C2 equals Q3 divided by C3. Now, since capacitors 1 and 2 have the same capacitance, that means that they will have the same amount of charge across them, so that when we do Q1 over C1, we get the same voltage. So I can say Q1 equals Q2, and then those equations reduce to 2Q1 plus Q3 is 3 times the charge we found in part A, and then Q1 is Q3 C1 over C3. So I got this last equation from setting this equal to that and solving for Q1. So Q1 is Q3 C1 over C3. So here I have 2 equations and 2 unknowns. I can plug in the Q1 from here into that equation, and I will do just that. So let me organize this a little bit. So I have 2 times Q1, so that's Q3 C1 over C3 plus Q3 is 3 times the Q that we found before. So I'll factor out Q3, and then I have 2 times C1, that's 8.4 microfarads, divided by 4.2 microfarads, plus 1 is 3Q. So this is 5Q3 equals 3Q. So Q3 then is 3 over 5Q. But we're not looking for the charge, we're looking for the voltage. So voltage 3 is Q3 divided by C3. So that will be 3Q over 5C3. So let's see what that is. So that's 3 times 7.56 times 10 to the negative 5 coulombs divided by 5C3, which is 4.2 times 10 to the negative 6 farads, and that is 10.8 volts. So the problem wasn't hard, except you had to remember how capacitors combine in series and how they combine in parallel. And the fact that in series they have the same charge on the capacitors because the same current flows through here, and in parallel you have the same voltage across capacitors, so the charge can move around and distribute itself so that the voltage is the same in parallel.